Good morning students. This class we shall going to discuss about 8085 assembly language programs. Before we are going to see what are the some basic concepts. I just recall it. So what is number system? There are four types of number systems: decimal system, binary number system, octal number system, hexadecimal number system. Decimal number system totally 10 numbers starting from 0 to 9. So the base is 10. Binary number system only 2 digits 0 and 1, so the base is 2. Octal number system 0 to 7, total 8 numbers, the base is 8. Hexadecimal number system 0 to 9, 10 numbers, after that A, B, C, D, E, F, so totally 16 numbers, so the base is 16. So the binary number system, the decimal number system, the hexadecimal number system can be represented as so 0 is hexadecimal. It can be represented in binary form, that is 4-bit binary form 000. In decimal form only for 0. So decimal number system it's represented as 0 1 2 3 4 5 6 7 8 9, then 1 0 1 1 1 2 1 3 1 4 1 5 1 6. Likewise you can add decimal number systems. So similarly for 1 is the hexadecimal, which is represented in binary form 0001 as 4-bit binary form, then decimal 1. So likewise you can add 0 to F for hexadecimal, then 0 to F for binary form, that is 0002 1111 for 15 in decimal. The next octal digit. One octal digit is equal to 3 binary bits. One octal digit is equal to 3 binary bits. For example, 75 is the octal digit, which is represented as 3-bit binary form. 7 means 111, that is 8421 pattern, that is 421 pattern in octal. 1 is, that is 11 for 7, 101 for 5. Similarly 124 for 3 digits, 1 for 001, 1010 for 2, 100 for 3. So it can be represented as 3-bit octal formation. The next 4 digits 7006. 7 means 111. The next 000 for 0, 000 for 0, 110 for 6. One hexa digit equal to 4 binary bits. One hexa digit equal to 4 binary bits. So 25 is hexadecimal number. So 2 is a hexa digit, one hexa digit which is equivalent to 4 bits 0010. 5 for 0101. Okay, next 1 2 3. Likewise you can to represent 1 2 3 for, then 500 9, which is represented a 4-bit binary form. 10101 for 5, 00040 is 0, then again 40 for 0, 1001 for 9. So this is can be represented a 8421 pattern. Simply you can express it 8421. That is BCD code, binary coded decimal format. The next data is 8 bits. So every data has 8 bits. Smallest number is 0, then largest number in 4-bit binary form 000 up to 111. So 1111 for 15, that is F. 111 for again 15, F. So the value of FF is 255. So smallest value is 0, then largest value for 255. The next address is 16 bits. Data is 8 bits, but our address is 16 bit. So smallest address is 0, that is 0000. Next largest number is FFF. Largest address number is FFFF. So 65,535 up to sorry 0 up to 65,535 is a largest number. The next ASCII, American Standard Code for Information Interchange, it is a 7-bit code. So the ASCII can be represented in characters 0 to 9, which is the ASCII value of 30 to 39, A to Z 41 to 5A, small letter A to Z 61 to 7A. The next grouping bits, a single digit that is 0 or 1 is nothing but bit or binary digit. Group of 4 bits is nothing but a nibble, one nibble. That is one 8-bit data. That is one 8-bit data. There are two nibbles, lower order nibble and higher order nibble. So both lower order and higher order nibble can be added. It represents one byte. So 2 byte, which is represented as one word, that is 16-bit. The next double word, then quad word. You can add octo, hexa word. The next representation of decimal 5. So 5 is a digit, which is the name is 5 for the decimal format, that is base 10, which is represented in 4-bit form, that is 0101. Then 5 for 8-bit format. The first 4 bits are 00, the next 4 bits are 0101. The next 16 bits format, that is 2 bytes. The next 32 bits for 00 until last 4 bits 0101, so that is 32 bits. Next, signed and unsigned numbers. So first, what is 4-bit binary, that is BCD, binary coded decimal, which is equivalent to decimal is 0. Then 1's complement is 0, 2's complement is also 0. So likewise, signed number and unsigned number, which is calculated for 0 to 15, as it represented as shown above table. The next high level language, HLL, C, C++, Java, Perl, Python, VB, etc. These are all the some high level languages. We know that. So in high level language can be represented English only. Some printf, scanf statements, while, do, for, if, continue, break, these are the reserved words. Then the high level languages can be user friendly, that's why it is easy understand and debug. In high level languages, compiler will do, or it interprets, or it translates high level to machine level language. It's the main thing of in task of compiler. Then machine independent. Machine independence means that is Intel, Motorola, Zilog and Clips. These are all the some popular company for developing processes. There is no one-to-one correspondence between high level language and machine level language. The next, assembly language. So assembly high level language, which is represented in English. In assembly language, half of English, like sub, one instruction, add, add, multiplication, mul, division, div, load, lda, store, sta, move one place to another place, that is transfer of data between register to memory to register, and then move immediate, mei, move immediate of data to register, or directly you import the data, move immediate. So these are all the some of English, like some of the instruction we represented in assembly language. The next, mnemonics. So mnemonics we can easily memorize, because so every mnemonics has 3 words. For example, sub, add, and then add some registers and then data. The next, difficult to use or write program, understand and debug, because it is a mnemonics or it is half of English, so that's why difficult to use. The next, program written in mnemonics is called assembly language. So assembly language programs only can written in mnemonics. So in whereas in a high level language, compiler to translate high level language to machine level language, but here assembler can translate assembly language program to machine level language. So that is the difference for high level to machine level language. There is one-to-one correspondence between ALP and MLP. There is no correspondence to HLP and MLP, but here in assembly language program there is one-to-one correspondence. So these are the some points for before we are going to enter assembly language programs. So these things are very essential. So remember these rules. So registers can be represented in alphabets, that is B register, C register, D, E, H and L. M means memory, E is accumulator. Then pair register, HL is a register pair. Each register can accommodate only 8 bits, that is 2 hexa digit. One hexa digit is 4 bit, another hexa digit is 4 bits, so 4 plus 4, 8 bits. So 8 bit data can be expressed as 00 to FFF, that is 0 to 255. Then hexa digits, that is 00H to FFF, 65,525 to 0 to 65,535, that is the largest memory location. Okay, this is the register pair. B for BC register, D for DE register, H for HL register, SV bar, stack pointer. Okay. Okay, next, some of the useful informations for writing assembly language programs. A equal to 45. A 45 is assigned to A. Here this is the assembly language instruction, that is 8085. MEI is a half of English. A is a register, then 45 is a data. 45 which is stored on A, that is move immediate of A means the data 45 is imported on A. Similarly, A equal to B. A which is assigned to B, that is B is assigned to A. So move A comma B. That means B, the content of B to transfer A. Content of B is transfer on A. That is B assigned A. The next, BC equal to 1, 2, 3, 4. So load register pair, LXI means load register pair. 1, 2, 3, 4 is assigned, that is load B, that is BC register. B for pair register BC. Then content of memory, memory to accumulator, load accumulator, LDF for load accumulator address. Then store content of accumulator in some address, store STA for store accumulator address. The next, A equal to A plus A. A equal to A plus A, that is add A, content of accumulator, A equal to A plus A. Then subtraction, then increment register A equal to A plus 1, which is incremented by 1. The content of A is incremented by 1, the content of A is decremented by 1. Okay, these are some useful information for writing 8085 assembly language programs. Okay, next we shall go to discuss 8085 instructions. 8085 instruction, there are different kinds of instructions supporting 8085. One is data transfer instructions. Here transferring data one place to another place. Move immediate register comma data, move immediate, move register to register, load register pair, load address, load accumulator address, store accumulator, store load in accumulator, load in register pair, that is LDAX, load in accumulator from register address, STAX, store accumulator at the register address, load HLD address, load in HL from address, store HLD address, store HL at address, exchange, that is XCHG, exchange HL and D. So these are all some useful data transfer instruction. The next second one is arithmetic instruction for adding, subtracting, multiplications. So here add and subtraction only done on 8085 microprocessor. So add ADD for add, SUB for sub. So add register, sub register. Similarly ADC for add with carry, SBB for subtract with borrow. Add immediate data, subtract immediate data, SUI, ACI add carry immediate, subtract immediate data. Then INR register, that is increment register, DCR for decrement register, increment register pair, decrement register pair, DAD for double add, DA for decimal adjacent accumulator. So likewise you can add logical instructions, okay. Next branching instructions. So branching instruction for um, jump, call and return. So jump carry, JNC for jump no carry, jump 0, jump no 0, JNZ, JP, jump, JMP for jump pointer, JP. So these are all the some branching instructions for executing 8085. Then last one is stack, interrupt and machine control instructions. So stack instructions, comma, interrupt and machine control instructions. Push and pop is a very famous stack operations. In and out, EI for enable interrupt, DI for disable interrupt, SIM set interrupt mask, read interrupt mask, no operations, HLT. So these seven instructions are included in machine control instructions. So these are all the some basic concepts you will see in theory part also. So this is very essential for writing 8085 programs. So after that we are going to write 8085 assembly language editor. So this is the 8085 simulator or emulator. This simulator you can use to assemble 8085 any 8085 programs. So this is the 8085 assembly language editor. After typing 8085 instruction we are going to assemble it. So immediately can create some mnemonics, hexacode, bytes, machine cycle and T sets. So how many bytes the hexacode will be stored? So each hexacode or mnemonics can be executed some machine cycles. So after that the machine cycles will be calculated based on the T states. So likewise you can add it separately for each instructions. So this is after assemble it. Now after assemble it directly the 8085 simulator can create these things. The next, this is the register area. Totally in 8085 B register, C register, D register, E, H, L, then memory, then accumulator. So these are all 8-bit register because 8085 is a 8-bit processor. So this is stack pointer, memory pointer, program status for PSW, program control PC, clock cycle counter, instruction counter. So every time the program counter will be incremented, immediately the address can be incremented. The next, serial out data, serial in data, interrupt request. These are all the interrupt pins. The next, sim instructions, that is set interrupt mask, read interrupt mask instructions. So next, this is the memory range. So total memory range is starting from C0002 CFFF. So these are all the some total memory. So entire memory content. Suppose if you want loaded memory location, here go to store directly visible memory location. User want to assign some memory address. Here you can put the memory address and also you can give values. So this is 8085 simulator. So now we are going to see one small program for adding to 8-bit data. This is our first exercise in 8085. First all of you listen, then I will explain one by one for 8085 addition. The first instruction is MV high, that is move immediate A comma 89. So 89 will be imported on A, that is directly imported on A register. That's why move immediate. I am using move immediate. Okay, next. So this means A equal to 89. 89 is assigned to A. Okay, next. Add immediate. ADI means add immediate data. C5. C5 is a data which is added to content of A. That means the meaning is A equal to 89 plus C5. 89 plus C5 equal to 4 4E. 89 plus equal to 4E and carry 1. The meaning of instruction is ADI C5 means content of accumulator plus content of accumulator, that is 89. Before the 89 will be stored on A. 89 plus C5. For adding these two data, then the result will be stored again accumulator. So this is the meaning of this instruction. Okay, next. So after adding this data, then store it, that is ST for store, A for accumulator. Store accumulator some memory address. The memory address is starting from C000. So I am storing one memory location, that is C040. If you want to store any memory location below, that is starting C32, C30, C40, C50, but C000, C010, C020 are occupying some instructions. So you can select C42, C50, C60, C70 and add any memory location. Then C040. This is for storing only addition bit. Then carry bit will be stored on, that is move immediate A comma 00. So after adding these two data, the result will be stored on accumulator. Then the carry bit will be stored again in the accumulator. So that's why I'm freeing the accumulator memory. So 00 will be imported on A. So A, now the A is 0. Now the A is 0. Okay, next line. Add carry ADC for one more instruction, arithmetic instruction ADC for add carry accumulator. So before accumulator is 0. So now after adding 89 plus C5, if you get any carry bit, the carry bit will be added, that is A equal to 0 plus carry, because A is 0, that is accumulator is 0 plus the carry bit will be produced to add 0 plus 1. Again the result will be stored on accumulator A. So the meaning is A equal to A plus carry, that is carry bit. So now the carry is stored on some memory location, that is store accumulator. The very nearest location, before I am taking C040, the next nearest location is C041 for storing a carry bit. Then finally to stop the program. So this is our one simple exercise for adding two 8-bit data. Now go to assemble it. So after assembling the program, automatically it creates hexacode, that is opcode. This instruction is 2 bytes, that is move immediate A comma 89 is a 2 byte, which is executes 7 T states. The 7 T states which is equal to 2 machine cycles. So STAC040, so this is 3 bytes instruction which is executed on 13 states. So we need 4 machine cycles. So likewise it will automatically creates hexa codes, bytes and machine codes and teach states. So this is 50% of work is complete. Now we shall go to step by step process. So directly to run, or you will check step by step. First I forwarded, that is move immediate a comma. Now listen carefully, move immediate a comma 89. After executing the program, the value of accumulator is 0. After forwarding, the first instruction will be executed. Now it changes 89. So accumulator, that is move immediate a equal to move immediate of a comma 89. So a equal to 89. The next instruction add C5. Add C5 means a equal to a8 plus C5. So adding those data, that is C5 to 89 to C5, 89 plus C5, the adding, that is the adding bit, the resulting bit is stored on accumulator, that is addition bit. The next, here some carry will be produced. You see that cy carry equal to 1. This carry bit will be stored on some memory location. So that's why the next instruction is move immediate a comma 00. First the accumulator is 4e. After executing move immediate a comma 00, the accumulator becomes 0. Then the carry bit will be added, adc a. So the carry bit will be added on here. The carry bit will, before executing the instruction adc, carry bit equal to 1. After executing this instruction, the carry bit will be goes on accumulator, that is a equal to a plus carry. The next instruction stored on carry bit is very nearest location of C040, that is C040, that is addition bit, 01 for carry bit, C041 to location. So this alt for stop. So this is our memory location for adding two 8 bits data. This will complete one exercise, 8 bit addition. Similarly for 8 bit subtraction, the only change is add immediate to replace, subtract immediate. So here add immediate to replace SUI for, here you can change SUI for subtraction, SUI for subtraction. The only thing ADCA for, that is move, there is change, wait, here you can change SUI subtract immediate, for SUI to SUI for subtraction. The only change is there, ADI add immediate. Here you can change SUI subtract immediate for getting subtraction of 89 minus C5, subtraction of 8 bit data. To check this, what will happen, So any doubt, please contact. Thank you. Hope you understand. Okay, we will see you next class.